Welcome to the Math Record. Today I'll be covering indeterminates and Hopital's rule. So first off, what is an indeterminate? Well, indeterminates deals with limits, and there's 7 different types of them. It's 0 over 0, infinity over infinity, a 0 times infinity, infinity minus infinity, a 0 to the power of 0, 1 to the power of infinity, and a infinity to a power of 0. So there's 7 types, and if a limit comes out as one of these types, we could use something called Hopital's rule. And these forms are called indeterminants. So 0 over 0 and infinity over infinity, both of these do the same thing. So I'll just show you an example how to do this with Hopital's rule. As x approaches 0, sine of x over x. So first, you always have to check for any limit that you do. If you want to use Hopital's rule, you got to check that it's an indeterminate. So plug in your x equals 0 here, so sine of 0 is 0. And x to power x approaches 0, this x becomes 0. So 0 over 0 indeterminate. So it's indeterminate. Let's use L'Hopital's rule. L'Hopital's rules tell us that if it's an indeterminate, just take the derivative on the top and bottom separately. So derivative of sine is cosine. The derivative of x is 1. So that means the limit of cosine for when it's 0 is going to be 1. So that means if this is 1, then this is also 1. And that's basically it. So that means the limit of sine of x over x is 1. Now let's do a case where it's infinity over infinity. It's the exact same thing. The limit as x approaches infinity of e to the power of x over 2 to x. So let's say as we did before, we got to check that it's an indeterminate. So e to the power of infinity is infinity. 2 times infinity is infinity. So it is an indeterminate in the form infinity over infinity. So we can use L'Hopital's rule. So limit as x approaches infinity. L'Hopital's rule, derivative of the top is e of x, derivative of the bottom, that's 2. So that gives us that as we plug in x equals infinity, e to the power of infinity is infinity. Infinity divided by 2 is still an infinity. So that means if this is infinity, this is infinity. And that's basically it for the 0 over 0 and infinity over infinity case. Now let's deal with 0 times infinity, or infinity times 0, it doesn't matter what way you call it. So this, what we're going to do for these is that we're going to convert 0 or infinity, 0 times infinity to 0 over 0 or infinity over infinity. It doesn't matter which one because they both do the same thing as I shown before, as I shown earlier basically. So let's say we have the limit as x approaches 0 from the right, and we have x times natural log of x. So plug in 0 to check. So 0 times natural log of 0, which is infinity. So 0 times infinity indeterminate case. So we could use L'Hopital's rule. So we're going to convert it to 0 over 0 or infinity. So you can either write this as x. So if you ever heard of the expression dividing is the same thing as multiplying by its reciprocal, well, that's basically what we're going to do. So we're going to rewrite x times natural log of x as x divided by 1 divided by natural log of x, or we have natural log of x divided by 1 or 1 divided by x. And they both mean the same thing as this. So, so one of them is the 0 over 0, one is the infinity over infinity. It doesn't matter which one's which. Basically, this is the same thing. So what we want to do is choose one that's easier for us to take the derivative of. And this one seems much easier because this is a little bit harder to do. So we're going to rewrite this as the limit as x approaches 0 from the right, natural log of x divided by 1 over x. So if you want to check the case, you could, but we know for sure it's going to be indeterminate. So we plug in 0. Natural log of 0 is infinity. So 1 over 0 is infinity. So that gives us a indeterminate of the form infinity over infinity. So then we can use L'Hopital's rule. The derivative of natural log of x is 1 over x. The derivative of 1 over x is negative 1 over x squared. So this is the same thing as saying the limit as x approaches 0 from the right. 1 over x divided by negative 1 over x squared. Dividing is the same as multiplying by its reciprocal. reciprocal of negative 1 over x squared is negative 1 over x, negative x squared. So that simplifies to just negative x. And that will give that as x approaches 0, negative x approaches 0. That means this is 0, and that this is 0. So that means the limit of x times ln of x, natural log of x, is 0. And the next case is infinity minus infinity. And basically what we're going to do for these is that the difference between infinity minus infinity and 0 over 0, infinity over infinity, and 0 finds infinity is that these are combined to one term, while these are two separate terms. So to solve this, usually these are two separate things. We're going to have to combine them. So the limit as x approaches 0 from the right, 1 over x minus natural log of x. So we plug in 0, that's 1 over 0, which is infinity. Natural log of 0 is infinity, so infinity minus infinity, indeterminate case. So let's combine it. So if we multiply this side by x times over x, we could combine it using similar denominators. So that's going to be 1 minus x times natural log of x over x. And we know what this is. We just solved it earlier. That is 0. So as the limit as x approaches 0 from the right, that's 1 minus 0 over x, which is going to be 0 as x approaches 0. So this is 1 over 0. And 1 over 0 is infinity. Because what you're actually doing with limits is this is technically not 0. This is actually just a really small number close to 0. So 1 divided by a really, really, really small number is a really big number, which is a infinity. And that was the fourth case. Now the fifth, sixth, and seventh case, which is 0 over 0, 0 to the power of 0, 1 to the power of infinity, and infinity to the power of 0, they all deal with the same process, basically with exponentials. So let's say y is f of x to g of x, and we want to find the limit of like y, but what happens if they come out as the form 0 over 0, 1 over infinity, 1 to the power of infinity, or infinity to 0? Then it's kind of weird. What we could do is this way. So first, we're going to have to get the exponent down, take the natural log. So that's g of x times the natural log of f of x. Now what we're going to do next is that we're going to take the limit of both sides. Limit of g of x times natural log of f of x. And let's say that this limit comes out as some number L. Then basically what we're going to do now is that we're going to raise each of these. These are going to become our powers. And we're going to have a base e to all of them. So e to the limit of natural log of y is the same thing as the limit of e to the natural log of y, which e to the natural log of y is y, which is what we were looking for in the beginning. So that is equal to e to the power of our limit. So basically what we're going to be doing, as I shown in this process, if we're given this function, this basically equation, take the natural log of it, find the limit for that, and then raise it to a power, and then we're going to have e raised to that power. So let's do an example. So to end it all off, let's say we want to prove 1 plus 1 over x to the power of x is equal to e. So let's say using y is equal to 1 plus 1 over x to the power of x. Now if we plug in our, oops, sorry, I forgot the limit. Let me just move this around a bit. And we want to say the limit as x approaches infinity. And we want to prove that this is equal to e. So basically, we're going to set y is equal to 1 plus 1 over x to the power of x. And then we're going to evaluate this limit. So when we plug in the infinity to check that we could use L'Hopital's rule, we have 1 plus 1 over infinity to the power of infinity. So 1 over infinity is 0. To the power of infinity, 1 plus 0 is 1. 1 to the power infinity. This was one of our cases. As we said before, it was 0 over 0, 1 to infinity, which is what we have, or infinity to the power 0. So it's one of the three. So we could use this method. So from there, we're going to set y equal to that equation, and then we're going to take the natural log. So we bring our exponent down, natural log of 1 plus 1 over x, and then we take the limit of this. So the limit of x to the power of infinity of this entire thing. So what is the limit x approaches infinity of x times natural log of 1 plus 1 over x? Well, we plug in x equals infinity, that's infinity. And 1 over infinity is 0. 1 plus 0 is 1. And natural log of, natural log of 1 is 0. So this is an indeterminate of the form 0 times infinity. It's just written a different way. So then we can use L'Hopital's rule to write this as the limit as it approaches infinity. The easier one on the top is probably going to be this one, because we don't want that on the bottom. That's a little bit too complicated. So then on the bottom we have 1 over x. Okay, so L'Hopital rule said that since this is an indeterminate, basically we could use we could take the derivative on the top and bottom separately. So the derivative of the top is the derivative of a natural log is 1 over whatever is inside, so 1 over 1 over x. Since this is inside, we gotta chain it. So the derivative of 1 plus 1 over x, derivative of 1 is 0, derivative of 1 over x is negative 1 over x squared. So the derivative on the bottom, which is negative 1 over x squared, well, we cancel that out from there, so that just leaves 1 over 1 plus 1 over x. So the limit as x approaches infinity of 1 over 1 over x, we plug in 0 in here, infinity over here. So that'll be 1 over 1 plus 1 over infinity. So 1 over infinity is 0. So 1 plus 0 is 1. 1 divided by 1 is 1. So the limit of our natural log equation is 1. And as we said before, we just raise e to that limit. So it's e to 1. So that means y is e to the 1. And as proved, and that is true. Well, thanks for watching. And finally, this video concludes our chapter 2. And in the next video, I'll be covering the next main principle of calculus, the integral. See you later.